Hi everybody. This video is going to be on section 4.7, change of basis. There's going to be quite a lot of computation in this section, so I'm going to skip steps sometimes by just showing you the result of certain computations. I'll tell you how to begin, and then you can work through the actual row operations on your own if you like, okay? So let's start with a theorem. If V is a vector space, with basis V1 all the way to Vn, then every vector in V can be written uniquely. And that's the key word here, so I'm going to underline it, okay? Can be written uniquely as a linear combination of the basis elements, the basis vectors. Okay? Uniquely, that's the key here, okay? So it's sort of like every number can be factored uniquely as a product of prime numbers. Same thing, every vector can be written uniquely as a linear combination of the basis elements, okay? So it makes sense then for us to make the following definition. First off, the order of our basis elements matters. So let's create a new definition called an ordered basis. As you can imagine, all it is it's a basis where we keep track of the order in which basis elements are listed. Okay, so we need another definition here. If B, or let me back up a bit. Let me just say, let V be a vector space. And let B, which is V1 all the way to Vn, let this guy be an ordered basis. For V. Also, let V in V be a vector. So when you have a vector, of course, we know by the theorem above that it can be written uniquely as a linear combination. So suppose V is going to equal C1V1 plus C2V2 all the way to CnVn. Notice we have written it as a linear combination, and this is a unique linear combination, okay? So we call the constants C1 to Cn the components of V relative to the basis B. Components of V relative to the basis B. Also, we call, so abbreviate it this way. If you put a V with little brackets and a B there, we call this guy the component vector of V relative to the basis B. And you write it as follows. So it's going to be V relative to B, C1 all the way to Cn. So you just write it like that. In other words, we don't have to write all of those basis vectors. Essentially what we're doing is we're taking the fact that V is equal to this linear combination up here, and we're instead writing it like this, right? Notice that we're leaving out all the V's that make up the basis because the basis is written right here. So we know it's relative to those elements, so why bother listing it? Okay. So let's do a quick example here, okay? Just so that we understand this concept. Let's, of course, start by dealing with, a vector space that we're familiar with quite a bit. How about Rn? In particular, let's let V be R3. And what basis should we start off with? Well, let's let E be the standard basis. For V. What does that mean, the standard basis? Remember, this means that E is equal to E1, E2, E3. Another word for those, remember, is I, J, K, right? That's the standard basis for E. And let's let B be a different basis. This one's a little more awkward. Not as nice to work with, but we're using this to illustrate a point. 0, 4, 5, okay? Let B also be a basis for V. By the way, you can check that this is a basis by putting these as columns in a matrix and then taking the determinant and showing that it's not 0. It's also worth noting, and I should say that these are both ordered bases. Okay? Remember, basis is the plural for basis, so we're going to be using that word quite a bit here. Okay, they're ordered. In other words, I'm not going to change around their orders here, okay, for this problem. Okay, so how do we take another vector and write it relative to these bases? So let me start off by picking a vector. So let's let V equal the vector -11, 8, 22. Now, how do you write this vector relative to the standard basis? Well, that part is easy, right? Because we know how to write everything in terms of I, J, and K. Wouldn't this just equal, doesn't V just equal -11I plus 8J plus 22K? So, I mean, that's why we use the standard basis, because it's really easy to write elements in terms of it. So v is equal to that. So v relative to the standard basis is just going to be negative 11, 8, 22. So there's not really any calculation to do. When you want to write something relative to a standard basis, you just put it as a column vector. Okay? All right. So what about the other basis? So I want us to notice something here. Notice that if you take negative 3 times 2, 0, 1, minus 5 times 1, 4, 2, plus 7 times 0, 4, 5, you actually end up with negative 11, 8, 22, which is v. Okay. In other words, we took v and wrote it as a linear combination uniquely of those basis elements, and these are the constants. So this means that v relative to basis b is going to be negative 3, negative 5, 7. Okay? So that's how you write v relative to that basis, but this is how you write v relative to the non-standard basis that I randomly picked. Now you may be wondering how on earth I got negative 3, negative 5, and 7. So of course I knew those in advance. You're not usually going to know how to do that in advance, so you are going to have to solve a system. But I am going to demonstrate how to do that in the next example for a more complicated problem. But I just wanted to illustrate this definition. So now we understand what it means to write v relative to a basis. This also illustrates an important point here. The fact that when you have a vector in Rn, the fact that it always can just be written as a column vector, and that is always v relative to the standard basis. And so that's so important that I want to write that down. So if we generalize the last example, so if E is the standard basis for Rn, V, and V in V is any vector Actually, let me not call it V. How about I just call it Rn, just so we're clear on what we're talking about here. And V in Rn is any vector, then V relative to the standard basis is just going to be itself as a column vector. Okay, so there's nothing to change here. Okay? Just like in that last example. In other words, you can do this for more than just R3. You can do it for any n. Okay. Let's do a more interesting example here with a non-standard vector space. So, example. How about we use degree 2 polynomials? So first off, let's say let p of x equal to 1 minus 2x plus 5x squared, which we know is inside of P2R. And let b equal to 1x squared and c equal to as follows, 1 minus 2x. Oh, you know what? Let me do this on the next line. I'm going to run out of space. And c equals to 1 minus 2x, 2 plus x, 2 plus x squared, b 2 ordered bases for P2R. So part A, find this vector we wrote down. Oh, sorry, Px. Find P of x relative to B. And part B is going to ask us to find P of x relative to C. Okay. Let's start with part A. You could see that because this basis is so nice here, remember, we're looking at this basis right here, okay? 1x squared. P of x, which is 1 minus 2x plus 5x squared, is clearly just equal to 1 plus negative 2x plus 5 times x squared. And actually, let me go ahead. Oh, you know what? Let me put in parentheses the guys I care about, actually. And I'm going to underline them in red, okay? You notice that the constants are the exact constants in the problem, right? Because this is a simple basis, isn't it? You could see here that our polynomial coefficients ended up just becoming our coefficients in the linear combination, right? And so what this means, this means that P of x relative to that nice, you can call this essentially the standard basis, right? P of x relative to the basis is just going to be the following vector. Okay? Now, of course, part B is the harder one. We want to find P of x relative to this basis. In other words, we need to find the linear combination that makes those basis elements add up to our polynomial, right? Okay, so let's do part B now. So for part B, we need to find C1, C2, C3, such that C1 times our first basis vector plus C2 times our second basis vector plus C3 times our third basis vector is equal to P of x, 1 minus 2x plus 5x squared. We know how to do that. This is just a system of equations, right? Okay, so think about it, right? This is just going to give us a system. Let's just do the singular coefficients first. This means that we need to solve the system C1 plus 2C2 plus 2C3 is equal to 1. Again, I'm just equating coefficients. Negative 2C1. Now I'm looking at the linear terms, right? So negative 2C1 plus C2 plus C3 is equal to negative 2. And I don't have any C1s if you look at the x squared terms, I don't have any C2s, and I do have a C3 here. So I have C3 is equal to 5. Okay. Now, if I put, this is the system we need to solve here, okay? So this is the 3 by 3 system, right? So we know how to do that, right? We just put it as a matrix. So that's really what we're solving. But then this means we can just use a matrix, right? We can use Gaussian elimination here. So this is all we're doing. Okay. Now, I want you guys to notice something, right? Notice that we have, where did these come from? Notice that this guy right here, I'll highlight. This guy I'm underlining ended up right here. The second guy that I'm highlighting ended up right here. And the third guy that we're highlighting ended up right here. In general, guys, that's how you do it. You just take the basis elements and you put them inside of your Gaussian elimination, the left side, essentially put it as a matrix, and then we're going to use row operations. And so here's the part that I'm going to do on my own. So if you do row operations, and you can do this on your own, but I don't want to show all the calculations here, okay, just as a matter of saving time. So you end up with 1, 0, 0, 0, 1, 0, 0, 0, 1, and then going to 1, negative 5, 5. So what does this mean? This means that P of x is actually equal to, and let's go back. If we call this, if we go back to our original vector, let me go back to my original basis, if we call this guy V1, and we call this guy V2, and we call this guy V3, what that means is that P of x is actually equal to 1 times V1 minus 5 times V2 plus 5 times V3. That's the unique way to write it. So this means that P of x relative to our basis, we called it C, relative to C is just 1, negative 5, 5. Okay. So, as a general rule then, so in general, to find a vector B relative to a basis B, you're going to use Gaussian elimination, right? So I'm in particular, I should say Gauss-Jordan, or I guess Gaussian elimination. To solve the system. You can take the column vectors of B and adjoin V, and try to turn that into the identity, and you end up with your answer, V relative to B. Okay, so that's what we did in this last example. You just take your basis and write it as column vectors. And this is important. When I say the column vectors of B, I mean be very careful and make sure that you put them in the right order here, right? So in other words, be consistent with your order. Like here, for example, there is no order of a polynomial, but this isn't going to work if you don't put all of your polynomials in the same order. So here I used ascending order, right? That's why, for example, I had, I looked at my 1, my 2, my 2, and my 1, and noticed that that is what I put as my first. So 1, 2, 2, 1, right? In other words, when you put each column there, they have to go, excuse me, they have to go in the same order as, if these are in ascending order, like each color here, this is in ascending order, this is in ascending order, this is in ascending order, so that last guy has to be in ascending order, right? As long as you're consistent, then you can just put them as column vectors, right? And then you can just solve it and get your correct answer. And that'll save you time for you to not have to write out the whole system like this, okay? You don't have to write all that out if you know what you're doing and you make sure you put everything in the correct order. And by the way, you can check your work here, okay? So if I were you and I were doing this on an exam, how would you check your answer? You could check if this statement is really true. In other words, is it true that 1 times your first polynomial minus 5 times your second polynomial plus 5 times your third polynomial, does that in fact equal V, the polynomial we care about? Or P of X as we called it in this problem. So you could check that and you'll see that it does work. Okay, I would do that if I were you. That's how you check your answer, right? So these actually can be checked, which is nice because that's not always true in the linear algebra class. But here you can check your answer. Okay, so let's keep going with this idea. Actually, let me let me go on this page here. So question. Given 2 ordered bases B and C for a vector space V, is there a way to convert? I'm going to put that in quotes, okay, because we don't know what that means yet. But is there a way to convert V relative to B to V relative to C? In other words, is there an easy way, if you know the components of V relative to B, can you convert it to the components of V relative to C in some way? The answer is yes. So the answer is yes. We need a conversion matrix. And what is a conversion matrix? So we're about to learn that in this next part here. Okay, so here's our definition. I called it a conversion matrix just now, but the official term is actually not conversion matrix. It's actually going to be called a change of basis matrix. Change of basis matrix, okay? But you can think of it as converting from one basis to another. So let's write out our formal definition here. So definition. Let V be an n-dimensional vector space with the following ordered bases. So we're going to say B is equal to V1 all the way to Vn, and C is equal to W1 all the way to Wn. Then the change of basis matrix. Change of basis matrix from B to C, the order matters here, from B to C, is written as follows. Okay, so yes, that's a weird way to write a matrix, but that is a matrix. That's the way your book writes it, so we're going to stick to that. We write it as P from B to C, but we write it backwards. B to C like that. And this is what you have to do. You have to take a matrix and you have to write all of the basis elements of B relative to the other basis C. And put them as columns in your matrix. Notice, by the way, because we're dealing with an n-dimensional vector space, each of these vectors have n components and there's n of them. So this, of course, is an n by n matrix, okay? An n by n matrix. So your change of basis matrix in an n-dimensional vector space from one basis to another is always an n by n matrix. Now, why do we care about this matrix? The important property, so the important property of this change of basis matrix is that if you multiply that matrix times any vector v relative to the basis b, it gives you vector b relative to the basis c. And this is true for all v in V. In other words, for any vector you want, if you know what its vectors, if you know what its components are relative to one basis, and you know the change of basis matrix, then you can convert it. Or another way to say that is if you know the change of basis matrix, then you can convert any vector relative to basis B to that same vector relative to basis C. Okay. All right, well, let's do an example here. Well, actually, maybe what I'll do, I want to write some general things here about how you actually find this change of basis matrix before we do the next example, okay? So, how do we find this change of basis matrix as efficiently as possible. So think about it. To find So remember, this change of basis matrix, as we said, is actually equal to V1 relative to C, V2 relative to C, all the way to Vn relative to C. But we know to find each Vi, we have to solve a system of equations, right? To find each Vi, we need to solve a system, right? What's the system going to be? The system's going to be C1. So I guess I should give the basis elements names, okay? We need to solve a system. So let me say it this way. If B, we already know that the B vectors are, this is just a reminder here. Remember, B, we're going to call the V's, and C, we're going to call the W's. So to find Vi, we need to solve a system. So what's our system going to be? Well, to find each Vi relative to C, right? That's what we're looking for. Right? We need to find each of these. We have n of these to find. How do we find them? So we need to solve a system. What's the system going to be? It's going to be C1 W1 plus, because we need to find out how to take a guy and write it as a linear combination of these guys, right? And you have to do that for each one. So we have to do it for V1, and then we have to do that n times. So in other words, we have to solve n by n systems. Right? This first system is going to give us V1 relative to C, and this guy's going to give us Vn relative to C, right? In other words, we're solving for the C's in each one of these systems. Now, this is a lot of work, but we already know, similar to how we found inverses, so similar to the Gauss-Jordan inverse method, we can solve all these systems simultaneously. Okay. So how do we do that? Start with your column vectors for basis C, and on the other side you put in your column vectors for basis B, and use row operations to get it to look like the identity. And then on the other side is going to be your change of basis matrix. Now you got to be careful here. I mean, here's how you can think of it, right? I mean, these are the column vectors of C. These are the column vectors of B. And so the way you can think of it is, you could think of it this way. But just be aware that this is not really C and B. These are, because C and B are bases, right? But the way you want to think of it is, you know, their vectors make up that matrix, right? And so that's what we're doing, is we're sort of taking their vectors, turning them into matrices, and then you can solve this using a single computation, which is very nice. So this is to find P, and now you can kind of see why they write it this way. The way that I always remember it is the order here, right? I mean, look at the order of the elements. We have, if you want to find the change of basis matrix from B to C, notice we write it in the order CB, CB, look, CB, same order. So hopefully that serves as a nice reminder for how you find this matrix. Okay. So I'm going to do a couple examples here. Let's let V equal R2, and let's let B equal 1, 2, 3, 4, and C equal 7, 3, 4, 2. Let's let these guys are ordered bases for R2. And what is our vector going to be? Our vector for this problem is just the vector 1, 0. Okay. So part A is going to be to determine V relative to B and V relative to C. And part B is going to be to find P, so change of basis matrix from B to C, and change of basis matrix from, C to B. Okay. Let's start with part A. How do you determine V relative to B? Remember, you take your basis elements of B, and here's our basis vectors, right? Our basis vectors for B, here and here. We're going to write them as columns in our matrix. So we have 1, 2, 3, 4, and we put our vector V in here, 1, 0, and we're going to solve this system. Okay, now again, we're going to do our row operations, and I'm going to do those on my own. I already did them, and I ended up with 1, 0, 0, 1, and -2, 1. So this means that V relative to B is the vector -2, 1. Okay. You can check that, of course, right? That means that -2 times this guy plus 1 times this guy should give you 1, 0. Okay? You could check that, it works. You can even kind of do it in your head. Okay? Now, so that is our first guy they asked us for. They also wanted us to find V relative to C. So we're going to take these guys here and put them as columns, right? So we have 7, 3, 4, 2, and we put 1, 0. And again, if we use row operations, we end up with 1, 0, 0, 1, and we have 1, -3/2. So this means that V relative to C is 1, negative 3 halves. Okay? So that's how you find a vector relative to a matrix. We already did that in the previous example, but now we're going to find the change of basis matrix in part B, which is new to this problem. So let's go ahead and do that. So for part B, let's start by trying to find, change of basis matrix from B to C. Remember, we're going to start by taking C and then B. In other words, we're going to take the vectors that make up C and turn them into the column vectors, right? So the column vectors for C were 7, 3, 4, 2. And then for B, it was 1, 2, 3, 4. Right? So there's C relative to, there's the change of basis matrix from B to C. Okay. So what do we end up with here? Again, I'm going to do these separately. So if I do the row operations separately here, I end up with 1, 0, 0, 1, and then negative 3, 11 halves, negative 5, 19 halves. Okay? So what that means is that the change of basis matrix from B to C is equal to negative 3, 11 halves, negative 5, 19 halves. Now we're going to find P from C to B. So we're going to put B and then C here. This means it's going to be in reverse. 1, 2, 3, 4, 7, 3, 4, 2. Okay? 7, 3, 4, 2. So if we do our row operations yet again, I'm not putting them here just to save time, but I do recommend you work the details out. Okay, you certainly do have to if you're doing the problem like this on an exam or something like that. You have to show your steps. So you end up with 1, 0, 0, 1, and then we get negative 19 halves, 11 halves, negative 5, and 3, which means that your change of basis matrix from C to B is equal to that guy. And so let's actually test it, okay? Let's test it. In theory, if I take this matrix, any of these matrices, and I multiply it by V relative to B, I should get V relative to C. So let's see what happens. So we're going to, this will be our check to make sure our calculations are at least consistent, okay? What's P, B relative to C times, what is our change of basis matrix times vector V relative to B? So what do we get? We had, remember, our answer was negative 3, 11 halves, negative 5, 19 halves. And we're multiplying it by, what was V relative to B? Remember, it was negative 2, 1, right? So if we actually multiply this out, we end up with 1, negative 3 halves, which is indeed V relative to C. So it worked. See how this change of basis matrix, multiplying it by V relative to B gave us V relative to C. So we were able to convert this guy to this guy using the matrix. Okay. Pretty cool. Now, I want you guys to notice something, because you may wonder, how are these matrices related? So how are P from C to B and P from P from B to C and P from C to B related, right? I mean, seems like these matrices might be related in some way. So I want us to try something. What happens when we multiply them together? P from B to C times P from B to C. Just as matrices, so P from B to C times P from C to B, change of basis matrices going in either direction. What happens when you multiply the matrices together? So remember, P from B to C was -3, 11 halves, -5, 19 halves. What happens if we take that matrix and we multiply it by the other matrix we had was -19 halves, 11 over 2. Oh, wait, hold on. No, wait. No, that's right. -5 and 3. Yeah. I think those were the two that we ended up with, right? Okay. If you multiply these two guys together, what do you get? You actually get the identity. You actually get the identity. Okay. Very, very cool, right? What does this tell us? This tells us that these two matrices are inverses of each other. Is that always true? Yes, it is. So this gives us a nice theorem. The theorem says that the change of basis matrix from B to C inverse is actually equal to the change of basis matrix from C to B. Okay. Very cool fact. We're going to do one more example where we use this fact. So, example. So let's let V be P2R. And let's let B equal 2 plus 4x plus x squared, 2 plus 7x plus 2x squared, 6 plus 4x plus 5x squared, and C is going to equal 2 plus x squared, x plus x squared, and x, and these are both ordered bases for V. We're going to find the change of basis matrix from B to C and use it to calculate change of basis matrix from C to B. Okay. So let's start by finding P from C to B. So to find B to C. Yeah. Sorry if I say it backwards all the time. I'm writing it correctly, but sometimes I'll say it backwards because I know they're written in reverse order and it's confusing, okay? So we start by putting C and then B. Remember, just be consistent in your ordering here. So what do I mean by that? I'm going to do it in ascending order again. So, right, if we write down C first, look at C. We have a 2, then a 1, then a 1. So I'm going to put it in that order, and I'm going to do that for this entire problem, okay? So first I put C in there. I've got 2, 1, 1, and then 0, 1, 1, and then 0, 1, 0. Those are the basis vectors for C. And then I have 2, 4, 1, 2, 7, 2, 6, 4, 5. Those are the basis vectors for B. And I worked this out, but I don't want to do all the math right now. So this is just going to be row operations. We want to get it to look like the identity. We end up with as follows. Oops, hold on. Yep. And so what we end up with on the other side is the following matrix. 1, 0, 0. Oh, sorry, no, not 0. 1, 0, 3. 1, 1, 5, and 3, 2, negative 1, which means that P, change of matrix from B to C, is equal to 1, 0, 3, 1, 1, 5, 3, 2, negative 1. Okay, so what about P from C to B? P from C to B is just going to be P from B to C inverse. So we could just find the inverse of the matrix we just found. So how do we do that? Remember our Gauss-Jordan method. Just take the guy we just found and adjoin the identity to it. And if we do row operations here, we end up with the following. 11 over 14, negative 3 over 7, 3 over 14, negative 8 over 7, 5 over 7, 1 over 7, 1 over 14, 1 over 7, negative 1 over 14. So this means that change of basis matrix from C to B is indeed equal to 11 over 14, negative 3 over 7, 3 over 14, negative 8 over 7, 5 over 7, 1 over 7, 1 over 14, 1 over 7, negative 1 over 14. Okay, so we got our two change of basis matrices. I'm not saying that this is easier, but it's just an alternate method for doing it, right? We now know two ways of finding a change of basis matrix. We could do it directly, or we could do it by finding an inverse, if we know the other direction, right? We got one more theorem I want to write down. We're not going to do any examples using it, but it is an interesting thing to note here. Well, actually, you know what? I think I do want to do one example with it, just because it is a really nice theorem. Let's let B be a vector space. With ordered bases. Now let's suppose we have three bases, A, B, and C. Then the following is indeed true. If you want to change from A to C, you can actually multiply the following two matrices together. So that makes sense, right? Think about it. If you multiply a vector, what would the proof of this be? It's a pretty simple proof, right? Because if you take this and you multiply it by a vector v relative to a, first you do this multiplication, you end up with v relative to b, because that's what a change of basis matrix means. And then if you multiply it by this guy, you of course get v relative to c. In other words, what that proves is that this matrix here, if I had done the multiplication in the other order, that this guy must be P from change of basis matrix from A to C, right? Because we multiplied it by this guy, and it ended up with this guy. Okay. So what does that mean? We have now an alternate method using the standard basis. Okay. So alternate method for finding a change of basis matrix is using the previous theorem and the standard basis E. In other words, isn't it true that I can just introduce E as an intermediary step? Okay, and we know that changing from B to E is going to be easy, okay? So this actually becomes like this. So this is just an alternate method here, but I do want to do a quick example using this alternate method just to show how we would redo the previous problem, and it becomes easier and we are going to get the same answer, okay? So we like this because the change of basis matrix from B to E is really just going to be itself, okay? So one of these two is trivial to find and the other one just requires finding a single inverse of a matrix. And I want to show you guys how this works, okay? So we're going to redo, let's redo part of the last example. So part of the last example using this trick. So remember our last example, I don't want to write out the problem statement, but remember we were asked to find P from B to C. And so instead what we need to do is we're going to, instead of writing that, remember what we just wrote. It's going to be P from B to E and then E to C. But E to C is really just C to E inverse. And then this is going to be B to C. So we basically need to find these two pieces, this guy and this guy. So let's start with the guy on the right. The guy on the right is the easy one, right? So, sorry, did I write B to C? I meant to write B to E. I apologize. Yeah, B to E. Okay. So let's start by finding P from B to E. But this is trivial, okay? This is trivial. Why is it trivial? Because remember, P from B to E is just going to be to find your column vectors of B relative to the standard basis, but that's just itself, right? In other words, it is going to be just B. Okay, so P from B to E is just going to take this is just given, basically, right? Here's B. We just took these guys and we put them as columns, and that's our change of basis from B to E. That's why using the standard basis is nice. 2, 4, 1, 2, 7, 2, 6, 4, 5. So there it is, okay? No work to do there. Now, what about P from, we know that P from C to E is of course the same thing. Just put those guys as column vectors. This was given, but we need to find the inverse of this. Okay, so what is this going to equal? That does take some work here. So we have to take 2, 1, 1, 0, 1, 1, 0, 1, 0, and adjoin the identity to that. And again, if we do row operations here, we end up with we end up with 1/2, -1/2, 0, 0, 0, 1, 0, 1, -1. And so that is our inverse matrix. And now we just need to multiply these matrices together, right? So sorry, this is P from E to C inverse, right? Sorry, C to E inverse, right? So now I just need to take this matrix and multiply it by this matrix, and I get my answer. So P from B to C is going to equal this matrix times this matrix and if you work this out, you actually do get 1, 0, 3, 1, 1, 5, 3, 2, -1. And if we look back at our last example, it's exactly what we got, isn't it? So let's write that down. Same answer as the previous method used in the example. Okay, so this basically gives us 3 different ways of finding a change of basis matrix. You can either put the bases inside and do the row operations, or if you know the other way, you can just find the inverse, or you can use this new method, which is to introduce the standard basis into it. Okay, as usual, we don't need to know all of these methods. You may need to do some of the homework problems, but usually just knowing the first method that we learned suffices. It's kind of the most direct way, right? So the way that we did it here, the way that we did it, let me go back here. Yeah. So this is sort of the standard method. This is the way that I would recommend making sure that you know. Although knowing the others is nice. Like if I give you one change of basis matrix and ask you to find the one going the other way, then finding the inverse of what I gave you is probably the easiest way, right? Because you could just do one single calculation. But in the end, this is one calculation anyway, so it's really up to you. But it's interesting theoretically how all these things are connected to each other. All right, everybody, thank you so much for watching. I know this was a very technical lesson. Hopefully, with being able to watch it slower or watching parts over as needed, things can become clear. All right, thank you for watching.